Hess's Law. So Hess's Law is essentially where we can take some known reactions to determine the delta H of another unknown or target reaction. And essentially what this is assuming is that the delta H for a process is not dependent on the pathway taken. So if you start at one particular point and you end at another point, it doesn't matter how you go from point A to point B or from those reactants to these products, the delta H for that process will be the same. Even if you go to point C in the middle or D or E or however many points in the middle, it doesn't matter. As long as you start at one point and you end at the other point, delta H is going to be the same. And so that's what Hess's Law is based on. Using Hess's Law. So when calculating delta H, we can use combinations of known reactions or reactions that we already know the delta H for. We can add them together to determine the delta H of a target reaction, or essentially a sum of these other reactions to figure out the delta H of a unknown reaction, which we're going to call a target reaction. So for example, you can start with these reactants here. So nitrogen gas and oxygen gas. And one reaction that you can do with them is that you can turn them into nitrogen gas and nitrogen monoxide. Another different reaction is that you can take oxygen and nitrogen monoxide and you can do a exothermic reaction and produce nitrogen dioxide. So those are two reactions. But what you could do is you could take nitrogen and oxygen and you could create, through this process, some of this NO2. And we could say, okay, well, that's the reaction that I want to do. It will have its own particular delta H. And if we take the delta H of this first reaction and this delta H of the second reaction, as long as we're starting with these as our overall reactants and ending up with these as our overall products, then we can use those two reactions. So this first reaction here and this second reaction here, we can essentially use those two reactions to figure out the delta H of this third reaction. So let's actually take a look at how that's going to look. So here's our target reaction. Nitrogen gas plus oxygen gas forms nitrogen dioxide. So we want to go right to the nitrogen dioxide. The question is, what is the delta H of that reaction? If we look at these two reactions here, nitrogen gas plus oxygen gas forms nitrogen monoxide as our first reaction, and nitrogen monoxide plus oxygen gas forms nitrogen dioxide. We can take those reactions and we can sum them together. So think of them as two equations being added together. What will happen is that the like terms will cancel out. So there's two nitrogen monoxides on the product side of the first reaction, which will cancel the two nitrogen monoxides on the reactant side of the second equation. All the other terms are going to, that don't cancel out, are going to carry through. If there's the same term on the same side, just like with any other equation, they're going to sum together and then they will carry through. Now, the reason why we do this is because the same thing that would happen for the species in the reaction will happen with the delta H's. And so essentially we'll end up with the delta H of a reaction that we've never had to do ourselves. And now we can say, okay, well, if you take nitrogen gas and oxygen gas to make nitrogen dioxide without even having to do that reaction, but by knowing these two reactions, we can add them together and we will get the unknown delta H for this third reaction. So essentially we're using known reactions to get this unknown reactions delta H, and we don't even have to do the reaction. So these reactions can be modified because not always do they add up perfectly, and so we want to play around with two things of them. The first one is reversing the direction of the reaction itself. So essentially we can flip a reaction around because we know how much energy is being produced by an exothermic reaction. Then if you just do the opposite reaction, we'd know how much energy is going in. It would just be an endothermic reaction. So the equation flips and the delta H also flips as well. If it's positive, it'll go negative. If it's negative, it'll go to positive. So for example, A plus B forms AB. Let's say that you required 10 kilojoules of energy to get it to happen. Then what we could do is we could say, let's flip this reaction. I'm going to write it as multiplying by -1. And what that will do is we get the same reaction. We've just flipped it. So the reactants are now the products are now the reactant, and the delta H, its sign gets flipped as well. Instead of being an endothermic reaction, it's now an exothermic reaction. Now, why we do that is because maybe we're trying to find a target reaction that has this as a reactant. Maybe AB is a reactant, and our original reaction had it on the opposite side. So we've got to flip the reaction around and do the same thing to the delta H. Modification number 2 is essentially the same thing, but instead of multiplying it by a negative or flipping it, we're going to increase the magnitude of the reaction. So let's say, again, we had the reaction A plus B forms AB, and it's an endothermic reaction of 10 kilojoules. If we wanted maybe 2 of these ABs to be on the, no, we don't want that. If we wanted 2 of these ABs to be on the reactant side, we could just multiply the entire reaction by 2, because we know that if you have one A reacting with one B to form one AB, it would be 10 kilojoules. So if we double the reaction, we just end up with 2 A's plus 2 B's would form 2 ABs, and the energy that went in would be twice the original amount. So we're just changing the magnitude of the entire reaction itself plus the delta H. And again, why we'd want to do that is maybe we have a particular target reaction that has a certain coefficient in front of the species. And so we'd multiply it by the entire reaction by that coefficient, including the delta H, so that we would get to our target reaction. So let's try this one out. 3 carbons plus 4 hydrogen gas molecules forms this propane here. And we want to know, okay, if this reaction were to happen, what would be the delta H? And maybe for a bunch of reasons, we can't actually carry out this reaction. Maybe it's difficult to do or it can't be done, but we still want to know what the energy involved would be in order to get the reaction to happen. What we could do is we could say, okay, well, I know these 3 reactions here, and they each have their own particular delta H's. So maybe I can manipulate them in a way that gives me my target reaction. So then we have to go through and see, okay, can I change these reactions, sum them together to get this overall target reaction? And if so, I'll know the delta H. So the first thing you want to look at is say, okay, well, I've got 3 carbons, and this is the form, a particular allotrope of carbon, solid carbon as graphite. So I have that species here, and it is on the reactant side, so that's good. But the problem is I need 3 of them. But that's no problem. I can just multiply that first reaction by 3, and then I would have 3 of them. But I've got to multiply everything in the reaction by 3, including the delta H. I've got to multiply that by 3 as well. And then I look, okay, well, my propane's here, and in this reaction I do have propane, but it's on the wrong side. It is one of them, so I have the right amount of it, but I've got to get propane over to the other side. So what I could do is I could take this entire reaction, including the delta H, so the delta H and the entire reaction itself, and flip the whole thing, or think of it as multiplying that equation by -1. The products would become reactants, the reactants would become products, and the delta H itself would flip as well. So instead of being negative 2,220, it would be positive 2,220. So that would take care of the propane and the carbon. Then I have the, let's pick an orange color here. I need 4 hydrogens on the left-hand side as well in order to get my target reaction. So if I look at this last one, I do have hydrogen, but it's on the correct side, but I don't have enough of them. I'd have to take this entire reaction here, and I would have to multiply it by 4. And I'd do the same thing to the delta H. I'd have to multiply that by 4 as well. Then I would have all of the correct species in the reaction. So let's have a look at what that will look like. So this first one I'm going to multiply by 3. And so essentially I get my 3 carbons, my 3 carbons, my 3 oxygens, my 3 carbon dioxides, and my delta H for that particular reaction, because I'm doing it 3 times now, is 3 times the magnitude. It's going to produce 3 times as much energy. Let's multiply the bottom one by 4. And again, the delta H gets multiplied by 4. And the middle one, we have to flip it, or let's say multiply by -1. And so we end up with the exact same reaction, just flipped around. And again, the delta H is also going to be flipped. Now, if I look, I've got the right amount of carbon, so that matches up. I've got the right amount of hydrogens, that matches up. And I've got my propane, so that matches up. So I have everything I need. I just also have to I want to check to make sure that the other species, because they're not in my target reaction, right? So I want to make sure everything else is going to cancel out. So I can take a look and make sure that's going to happen. On the left-hand side, I've got 3 oxygens and 2 oxygens. So that's a total of 5 oxygen molecules on the left-hand side. And that'll cancel out with 5 oxygen molecules on the right-hand side. Now, they have to be the exact same thing. So an oxygen molecule wouldn't cancel out with 2 oxygen radicals. They have to be exactly the same thing. As I say, 4 waters that we have right here will cancel out with 4 waters here because they're both liquids. If one of them was a gas, it wouldn't be the same thing. There would be a difference between them, and therefore changing that would require some energy, and so we'd need another reaction to get them to cancel out. To cancel out, they have to be the exact same term. 3 carbon dioxide gases are going to cancel out the other 3 carbon dioxide gases, and so I end up with all of the species I want on the left-hand side of the arrow here. My hydrogen will carry through, my carbon will carry through, my propane will carry down as a product, and then I need to do the same thing with my delta H's. I just need to sum all of my delta H's. And there we go. So we end up with our target reaction, everything that we wanted in our target reaction, and we find out that our delta H for that particular target reaction is negative 106 kilojoules. All right, let's try this one out. Again, our target reaction here is a particular reaction, and we can find out what its delta H is without having to do the reaction, assuming we can take some given reactions and set them up in a way that they will sum together to give us our target reaction. So taking a look at this, let's do our hydrogen. So if I want a hydrogen gas, I want one of them on the left-hand side. And looking at these equations, I have 3 hydrogens on the left-hand side here, and I have 4 here. So if I took this second reaction and I got the hydrogens on the product side, there'd be 3 on the product side, and I used it with this reaction, the third reaction here, I'd have 4 on the reactant side, so essentially that would cancel out. So let's say, okay, let's take that first one, and we're going to have to multiply it by -1. That would take care of our hydrogens. For our chlorines in our target reaction, the only equation here has chlorines on the reactant side already. So this last equation I'd want to leave as it is. I don't want to flip it. I don't want to multiply it by anything. So just leave it as it is. And then my HCl gas molecules, if I look at this first reaction, here they are here, but A, they're on the wrong side, and B, I don't have enough of them. So I'm going to have to flip the equation and double the amount. So if I multiply by -2, that should do it. So let's do that. The first one multiplied by -2, and we're flipping it, multiplying by 2, including the delta H as well. It is also being multiplied by -2. The second one we're just flipping or multiplying by -1, including the delta H. And third one we're leaving alone, so everything carries down, and we get our final delta H of -185. And again, we want to make sure everything that is not in our target reaction is canceling out. So again, if we look at nitrogen gas, it doesn't show up in our target reaction because it cancels out from the second equation as a product and the third equation as a reactant. Ammonia gas, it cancels out because the first one has it as a product and the second one has it as a reactant. And ammonium chloride is a reactant on the first equation and a product on the last equation, so it's going to cancel out as well. 4 hydrogens, 3 of them will cancel out with these 3 hydrogens here, leaving us still with 1 hydrogen, because remember the coefficients just tell you how many there are of each one. So we have 1 hydrogen, 1 chlorine gas, forms 2 hydrogen chloride, all carrying through down to our target reaction. Our delta H's summing together to give us our delta H of the target reaction.